All right, I think yep, we're back to recording. All right, so the next concept we're going to talk about, and sort of the subject of this next little section, is maximum efficiency through whole building systems design. And you'll hear it discussed in a couple different ways, and some people will say whole building design, some people will say systems design. The process of designing whole building design is also called integrated design. But the concept is you can't, when you're talking about efficiency, and whether you're looking at new construction and designing a new building or you're looking at an existing building, you can't think compartmentally when you're talking about the individual energy improvements or parts of the assembly, because the entire building is a system. And not only in trying to gain maximum efficiency, and the example for that is the sports car example, and you can put all of you put the most powerful engine with the most horsepower and the most streamlined body design and the right suspension and the right shocks, and if you put bald, nubby tires on it, you're not going to get the performance out of it. So you have to think of the building in the same context. It's not just improving one part of it, it's improving the whole system. And then the other part we'll talk about is understanding system design so that you can and do recognize the interaction of all of the building systems and avoiding unintended consequences. So how do we do that? First, we've got to look at and understand that the building does have several forces that are acting upon it. It's the building itself, it's the occupants and how they use it and when they use it, and then the environment itself. So again, thinking about designing a building, what might be the best building design for southern or southwestern Arizona certainly isn't going to be the best building design for Vancouver, British Columbia. You've got different forces environmentally acting on it, and then for the same thing, you can't expect to have the same systems and the same assemblies that might be effective for a university building to be as effective for a residential building, and vice versa. So not only just the building itself and the materials, but the other forces that are acting on it, such as the environment, the occupant. And the concept of it, the overarching concept of whole building design, is so that all the components work together and achieve an end result, not just a home, but a building that uses less energy, water, natural resources, creates less waste, and is potentially healthier for the people living inside. And as I said, the other part of it too is making sure that you understand that how the changes to one component or one system may affect the whole entire house or the whole entire building, and making decisions based on best practices and the most cost-effective of those best practices. And I'll talk a little bit and give you a couple examples too of things we call solution multipliers, and that plays along into the same context of the best practices. So why did we spend time talking about conduction, convection, radiation? We'll talk a little bit more about moisture migration today. Why do we go through all those building science concepts? Primarily, as we start to get into whole building systems design, it's because the physics of all of those act upon not just the systems but the assemblies that we use. And if you've got an understanding of how the physical sciences play out on your building assembly, you can achieve the maximum efficiencies with hopefully avoiding any of the unintended consequences. when it comes to design in new construction, I did mention the integrated design process. What becomes important, and especially when you start looking at larger scale buildings, having a knowledgeable team involved in the whole process, understanding how the systems work. And we're not going to spend too much time talking about that, but you'll see on our site visit, and we'll post some video of it when we do, and you guys that are in the classroom here can see over there are the plans for the Missoula College building, the new Missoula College building. And there are 3 sets of plans over there that are all about 1/2 to 3/4 inch thick, probably 60, 70 pages in each. And so having a knowledgeable team working together with the understanding of the building science is how you can get that whole building efficiency. It's really beyond the realm of any one person to be able to understand and design the building envelope and the mechanical system and all the electrical and lighting systems and efficiencies and the hot water delivery. So it's a big part of whole building design. Just an example again of how all of these things are connected, and we're not going to go through all these things. You can see those on the slide. But suffice to say, there's a lot of different systems that are involved when we talk about whole building system designs. So what are the major systems? When most of the systems design programs and people that promote system design, you'll see the systems broken out this way. There's the envelope, and one of the most important systems when it comes to efficiency. So what components make up the thermal envelope, the walls, the roof, the windows, the doors, everything that makes that thermal separation from the inside to the outside. The other major system is your heating and your cooling system. This includes all of your furnaces, air conditioners, boilers, any heat capture, heat recovery systems. The next one is your ventilation system, so fresh air in, stale air out, and how that's all distributed throughout the building. Domestic hot water, and not only the heating of the domestic hot water, but the delivery of it, and then capture or recapture of some of that hot water heat can be a big part of efficient system design. And then both your interior and your exterior lighting system. Plug load and appliances. And then any of your process loads. And here again, when we talked about energy use intensity, you could see some of the different building types, and I don't know if you noticed, food service and restaurants had a pretty high energy use intensity. One of the reasons is because they've got pretty high process loads. They've got ovens and dishwashers, and they've also got a lot of domestic hot water heat. But the concept here really is that you've got to address all these systems, but you also have to make sure that the decisions you're making in one system are at least complementing, if not benefiting, parts of the other systems, and also not creating any unintended consequences. So look for solution multipliers that solve multiple problems or create multiple efficiencies. The biggest example of this in a solution multiplier is being able to increase the performance of your thermal envelope can oftentimes decrease the size of the heating and cooling equipment that you need. So if you can reduce the BTU load of a building, you can significantly reduce the size of the heating and cooling equipment. And this has to be evaluated systematically in the most cost-effective manner. Obviously, you can spend a significant amount of money to increase the thermal envelope, but at what point is it diminishing returns? So, for example, in a small residential home, you may be able to reduce, for example, the one they had in there was about 116,000 BTUs. Maybe you can make some improvements in the thermal envelope, and you can reduce that down to 90,000 BTUs. And if it costs you $1,000 to do that, and you can reduce the size of your heating equipment, you can go from a 120,000 BTU furnace to an 80,000 BTU furnace and save $600. You're probably it probably makes sense to do that. You're still paying a little bit more for your thermal envelope, but you reduce the cost of your heating system to about 60% of that cost, and then that heating system, because it's smaller, is going to be more efficient to run, so year over year you're going to save money. Where it really starts to make sense is when we're not talking about a 1,700 square foot house, but when we're talking about a 150,000 square foot commercial building. If you can spend a percentage to increase your thermal envelope, reduce not only the size of the heating system that you need, but you can reduce the size of your air handling and your ventilation. You can reduce the size of all of the thermal delivery in the building, and then recognize that savings year over year. So in a large building, maybe a 100,000 square foot building, it may take $500,000 to improve the thermal envelope and save 20%. But a 20% reduction in the heating equipment might save $300,000 and then save $75,000 a year on your heating costs. So finding those solution multipliers that can benefit multiple systems. And then watch out for solutions that might have unintended consequences. And this is really, we'll talk a little bit about moisture profiles and vapor drive more in depth than you guys have gotten into, but that's really one of the biggest examples of that. And it happens a lot in existing buildings and existing building weatherization. And in the desire to create greater energy efficiency, what will happen a lot of times without a good understanding of building science, you'll see people that will tighten up the building envelope and create significant unintended consequences. Not understanding where the vapor drive goes, and sometimes even creating potentially harmful situations. You can close a building up really tight, and if there's it's still using natural draft combustion equipment, you can have a situation where you've got excessive carbon monoxide buildup. So just understanding and looking at the whole thing as a system. Here's just one example of, this is a building at University of British Columbia, and one of the things they did was spend extra money to create this whole solarium area in the central hallway, increase the amount of natural light. And so with this natural light, and they also put light controls in, they reduced their overall lighting load. They were also able to, because of passive solar gain out of this, downsize their HVAC system. So as a solution multiplier, they put extra investment into having this in the design, having the thermal benefit of it and the reduction in the electric load, because they just didn't need to have as many lights in there or have as many lights on. So it was about a dollar for dollar wash in what they had to invest extra in the design and the structure to do this versus what they saved in downsizing the heating equipment and reducing their electric load. But now they continue to save that year over year with smaller electric load and smaller heating systems. This is another one. and part of what they did, this Center for Interactive Research, they were specifically looking for ways to add these solution multipliers into their building. And one of the things they did was create their own on-site sewer treatment. And this wasn't actually in the building, this was in an anti-building next to it. But they were able to significantly reduce the amount of water that they had to send out to the sewer treatment plant. And the way that they paid their sewer bill was by how much they were metered. Just as water coming in, they were metered on water going out. And they ended up, by having this on-site sewer treatment system, and then this pre-treated water ended up being used for irrigation on site, they reduced their annual sewer bill by about $17,000. They had about $40,000 invested in this system, and so it had a payback of just under 3 years, and then not only reduce their water use but reduce their costs. Yeah, so that's the whole concept of systems design. And again, we're going to go through and drill down and look at all the different systems, and try not to forget as we go through there, and I'll try to keep reminding you, try not to forget and get stuck in the minor details of each one of these systems, and understand whether it's what we're talking about here in new design, or as we go out and start looking at existing buildings, understanding that if you're going to take a certain approach, whether your approach is going to be to add insulation into this wall system, understand that that's going to have a cause and effect to all the other systems in the house. So is it going to create a positive solution multiplier? Is it going to help reduce the heating load? Is it going to help the occupant comfort? Or could it be creating an unintended consequence? But trying to keep that in the back of your mind when you're thinking about all these different systems. So what are some of the major strategies? And we'll get a little closer and drill down into each one of those, and we'll talk about the thermal envelope today. But basic strategies for whole building system efficiency in the envelope include highest R values and lowest U values possible. We'll talk about that in the thermal envelope. But again, if you have an exterior wall assembly that's not losing conditioned air to the outside, you're going to create the greatest efficiencies. Advanced framing, we talked about that in a wood cavity frame situation. If you can spread out the framing members, if you can reduce the amount of wood or reduce any amount of conductive material inside the wall cavity, you're going to increase the amount of insulation. We'll talk a little bit about windows in a minute, and then won't spend too much time on it, but briefly talk about where not just the type of glass that you use in a building, but where it goes and how much of it you use. We can get significant gains out of passive solar just by how we orient the long axis of the house. Then with that high performance building envelope, keeping it tight, keeping the air infiltration to a minimum, and then as I mentioned, passive solar design. We spent a bunch of time talking about that in 282, and we're not really going to visit a whole bunch on that. It is an energy efficiency concept, very big in the overall green building programs that we discussed. But in a residential aspect, just by getting the majority of your glazing on the south-facing side and having the long axis of your house face south or within about 15 to 20 degrees of south, just by that orientation without adding insulation or air sealing or anything, a house will perform about 15 to 20% better. So in this climate zone, passive solar can be a significant gain. We'll talk a lot about heating systems next week. We're not going to get into those this week, but Again, not just getting the highest efficiency equipment, but making sure that that equipment is the right size for the building load. Again, we'll spend more time on that, but equipment that's actually too large for the building can be far more inefficient than undersized equipment, and we'll talk about that. Good quality install with all of our mechanical systems, and then the sequencing of operation and how it's controlled. And that's another one that we're seeing more and more commercial buildings go back, not just in retro commissioning and trying to get the building envelope tightened up, trying to get greater efficiency in the equipment that they have, but greater control in the sequencing of it and the operation of it so that it's operating at the maximum efficiency. And we'll talk about that in a couple weeks, and we'll look at automation and building controls. Ventilation systems, having just like the space heating and cooling, having the right amount of ventilation, not too much, not too little. Most older buildings really were built on the premise of making sure that there was plenty of natural ventilation, and this was done either through poor leaky construction or just over ventilation of the building. In domestic hot water systems, we'll talk about again, it's the equipment and it's the high efficiency of the equipment, but it's also how it's operated, how it's delivered, and we'll talk a lot about in hot water, and especially when we start getting into multifamily and larger commercial buildings, you can save a significant amount of energy in how you design the hot water delivery. If you think about a 10-story building, and if you've got all of the hot water delivery equipment in the basement or on the roof of that 10-story building, think about how much pipe has to be put in that building to deliver that hot water to all the different points of use. And that hot water sits in that pipe for hours and hours and hours at a time and doesn't get used, so all it does is sit there and lose heat. So again, efficient operation. Same thing in lighting, and back to one of the things that we're seeing much more in new design now is daylighting strategies and daylighting modeling. We'll look a little bit about that later in the class, but if you can create, using passive solar design and using windows in the right place, if you can create a situation where you're getting enough daylight inside the building where you're not necessarily going to need as much of the overhead lights. And then just designing the right amount of lights. Plug loads, and here's one, we'll talk a little bit about this later, but here's one that really is surprising how much energy we waste on things, everything from phone chargers to computers to, when those things are plugged in, just because they're not on doesn't mean they're not using energy. So we'll talk about that both in occupant behavior and in systems, and then the process loads. So again, there's strategies in each one of these system areas, and they all have to be explored, and they all have to be designed and considered in relation to all of the other systems. One example, and talk about unintended consequences, was a particular retrofit project, and they really hadn't done any energy modeling, but they decided they were going to go in and replace all of their incandescent lights with fluorescent lights, and they replaced all of their every single light bulb in the entire office, and it wasn't a large office building. It was about a 4-story office building, and they realized their first winter there, their heating bill went up by about 15% because the incandescent lights were actually, the CFLs don't throw off any heat. where the incandescent lights were throwing off a significant amount of heat, and they discovered that by switching out to all the CFLs, their heating bill went up about 15%. So the money they thought they were saving by replacing all of their incandescent lights for the CFLs went out the window, because the CFLs were actually helping to heat their building. This is just an example in getting to net zero energy, and what in net zero energy buildings, considering a number of net zero projects, what were the strategies that they employed? And it's just an interesting one because, again, the daylighting and the high efficiency lighting were actually a part of every single net zero building just about. So, basic overall strategies for the envelope: high R, low U, advanced framing. We talked about this before. I think we should have gone through all of this already. You're all familiar with the U value and R value, so you understand they're both, the only difference between U value and R value, one is just the R value is rating material for its resistance to heat transfer, and U value is rating material for its transmission of heat through it. They're the same thing, they're just the inverse of one another. Just understand, for some of the calculations, if you get into doing any kind of energy modeling, and you'll see it a little bit when we work with ResCheck, a lot of what we do ends up getting converted into U value, so we can get the total U value of an assembly. So we can take all of the components and add those components together. We'll talk about solar heat gain coefficient in Windows mostly. And we'll talk about that in Windows and why that's important. Just some more definitions, and then emissivity, and I think we went through that again, but we'll talk about that in Windows in low emissivity and low E glazing, and how that helps control the radiant heat through Windows. So in looking at the thermal envelope system and the high efficiency envelope, there are really 4 basic steps in achieving high efficiency in an envelope. And the first is simple envelope design, and then the second is the right insulation. The third is having that insulation in contact with a complete air barrier, and then the final is to test and correct. So the first part of it is just locating the thermal envelope and understanding where you have that barrier between the inside and the out. We talked a little bit about it last week, but understanding where the air barrier is, and then making sure that if you have, especially with a fibrous insulation, making sure that you've got it covered on all 6 sides. So again, in a cavity wall situation, limiting airflow in that thermal envelope is critical. And the most effective way to do that is to make sure that your insulation is in contact with your air barrier. But back to that first, creating a simple envelope is one of the things in design that's pretty critical. You know, any place that you have an intersection of building materials, whether it's where a window connects to a wall, where a floor connects to a wall, where a roof connects to a wall, floor connects to the foundation, any place you have a connection, you have a weak spot. Any place you have a change in direction, you have a weak spot. So creating the simplest thermal envelope that you can removes more choices or more opportunities to make a mistake in that thermal envelope in the connection. And just for an example, here's one. You know, this is a pretty straightforward thermal envelope. It's fairly easy. You have a very good chance of, if your installation is correct and you're diligent, you have a very good chance of getting a good seal between the window and the walls. With proper detailing and installation, you can get continuous air barrier right through that rim joist all the way up around the ceiling and back down. It's a pretty easy thermal envelope. Inversely, and you'll see this in a lot of older houses and even some newer homes, but when you've got a lot of direction changes, when you've got, and these are all in your book, you can go through, you'll see a lot of these conditions in better detail in your book as well, but anytime you've got an interruption or a connection of two different materials, you've got a weak spot in the thermal envelope, and you've got a chance for bypass of air. So again, in going through and creating the air barrier, and especially when we're looking at cavity insulations. So if you read through your book, you saw the different types of insulations, and when you've got a fibrous insulation like fiberglass or cellulose or anything that allows a significant amount of air movement, it's going to be increasingly more effective if you've got a continuous air barrier. So primary air barriers can consist of a lot of different things. Exterior sheeting, house wrap, seam sealing, and interior drywall. We'll talk a little bit in a minute about where the air barrier goes, and that's one of the things that is important in looking at. It's going to depend on your climate zone. So in this climate, where do we want to put the air barrier? We talked about this already. Where do we want to stop our air movement?
Exterior.
The exterior? It does. I mean, if we have cavity insulation, we want to stop the air outside too, but it's more important to stop it from the inside. So if we, in a wall assembly for a building here, if we use the exterior sheathing as a primary air barrier, what can happen? What's that? You can have convection. You can have air moving through the wall cavity. And what else is moving? Moisture. So again, understanding where it needs to be. Most of these are listed in your book, but we'll go through them really quickly. A couple things, regardless of what the air barrier is, lapped and taped at the joints. So if you're using a polyethylene air barrier or if you're using a house wrap, making sure that it's complete. We'll look at some of that in some real-world projects right outside. Drywall glued to the studs. These are all in your book. Keeping that in close alignment with your insulation, taping and caulking all your seams, caulking, foam sealing the outlets, any penetrations that go through the thermal envelope, windows and doors. It's probably hard to see from there, but when you download these slides, you can see all the little problem areas. And I want you to look at this picture when you get a chance, because when we go out and start looking at some actual houses, you'll find most, if not all, of these conditions in one place or another. Joist bays, so again, we already talked about this, but where the floor joist intersects the wall, remember the difference we talked about between balloon framing and platform framing? That section where the floor joist, in a platform framing situation where the floor joist interrupts the wall, that cavity gets interrupted, pretty notorious for air barrier interruptions. Talked about the outlets, the return outlets, the soffits and the chases. The backside of tubs, and I think there's a good picture in your book on this one. A lot of times in bathrooms, the shower or the tub's on the exterior wall. and it gets put in before insulation ever happens. And in a lot of old homes, you'll find there's absolutely nothing between the tub and the shower and the exterior wall. So there's another area to look at when we're doing our weatherization. Between the house and garage, all the plumbing penetrations, any of the electrical penetrations. I just actually was in a house last weekend and where it was in the basement. The basement was sparsely insulated, but there was a hose bib going to the outside, and they had chiseled a hole in the concrete about that big, and you could see right out and see the dirt and the stones backfilled up against the side of the house. Recess can lightings, and there's a couple pictures of these in your book, and we'll talk about those a little bit too. Any penetration into the ceiling, and especially with recessed cans, what you'll see a lot of times, not only will there be a hole in the ceiling that's not properly sealed, and so you've got air infiltration around it, but also in a lot of applications, they just shove the recessed can up against the fibrous insulation so they completely condense it. And if you remember in your book talking about the R value of different insulations, and especially with the loose fill, as you change the density, you change the R value. So there's a point where with fiberglass and cellulose and ragwool, cotton, any of those loose fill insulations, they need a certain amount of density to achieve their effective R value, but if they get packed together and get too dense, then all the air spaces that are in there that are actually working to help create that resistance, all of those air spaces get condensed, and then their R value starts to go down. That's another one I've seen in some older homes that have, over the years, had some work done on them. One in particular, a homeowner was very proud of themselves because they had taken in a 4-inch space where they had 3.5 inches for cavity insulation, and they had managed to shove 3 layers of fiberglass into that area, and they thought they had an R33 wall because they shoved and compressed 3 layers of fiberglass into that wall, but they got rid of all of the fibrous properties in the air spaces in that insulation, and they may have had an R11, which they would have had with just 1 layer. So again, just these are basic strategies for a thermal envelope, and current code for us at 50 pascals is at least 4 air changes per hour. If you look at most any recommendations, Energy Star, any indoor air quality recommendations, anything less than about 5 air changes per hour, they highly recommend having mechanical ventilation. So any 4 air changes as to what our code is here in Montana, for occupant safety, it's recommended to have mechanical ventilation. So, for example, if you're going into an older house and you're going to go in and do some air sealing and add some insulation and weatherize, and for all intents and purposes, just in the spirit of greater efficiency, you probably are going to create much less heat loss. But if you get it down below 4 air changes per hour, you can be creating a situation that's potentially hazardous to the occupant. So again, looking at systems design, you can't just go in and say, okay, we've got $1,000, we're going to put $1,000 worth of improvements into the building envelope, and we're done. So. We talked about advanced framing. And one of the books that I recommended, and I think we talked about it last week, but they're climate zone specific, and they're Builder's Guide to Cold Climate, Builder's Guide to Mixed Humid Climates, but they have an incredible wealth of details in them. not just in how to build, but how to insulate existing details. And especially for weatherization and working in existing buildings, being able to go into an existing building, and if you're doing a blower door test and you're doing thermal imagery and maybe you're doing some smoke testing, you can usually find a lot of the areas that need to be insulated and sealed, but they're not always, finding the right path to actually do them is not always the easiest. We'll get more involved in this, and one of the things that you've got that I'll post on Moodle for you to do this week, and we're going to start working on after next week when we do our blower doors, is the Energy Out West Field Guide, and that's got a lot of conditions for existing homes and how to seal them up. But there are so many different methods that we've used to build over the last 50 or 100 years that there are a lot of different conditions out there that need to be sealed. So we talked about R value. The other thing that's in your book that we haven't talked about yet was permeability. Did you talk about permeability with Brad? Did I miss that one? Okay. And this is both important for air and for moisture, and then we'll get more into the moisture in just a minute. When it comes to air barriers, they're rated either as permeable or impermeable, and for insulation purposes, some of the foam insulations are the only ones that really have a perm rating where they become air impermeable. Even your foam sheeting that you put on the outside of the house is not completely air impermeable. And that's in your book, so you can look at the different ones on there. Again, yes, we're trying to eliminate infiltration through the envelope. One of the things too, just a quick side note, oftentimes the Tyvek that we see on the outside of the house wrap, it will stop a lot of the natural air flow in and out of the building cavity, but most of the house wrap actually does have a perm rating that really makes it air permeable. The house wrap that we put on the buildings really is designed to be a water resistant barrier to keep bulk moisture off of the sheeting. It's not designed to be an air barrier. So, what's that?
So is that gluing, the airtight drywall?
The airtight drywall approach, yeah, it's similar to a gasketed approach, but that's for putting an air barrier on the inside, and you're physically putting an adhesive on every stud to glue the drywall to it, so you're effectively closing off the whole cavity. It's one approach to get an absolute air barrier on the inside. It's very difficult to get it right, and it's very labor intensive. We'll talk about the last part, and what we're going to talk about are vapor profiles in the wall assemblies, and more and more as we start to get the buildings tight, building science is driving not so much anymore. We kind of went from having these leaky open buildings and air and moisture in and out in a fairly uncontrolled manner. In the name of efficiency, we went to really getting the buildings as tight as we possibly could, and that was probably the one that created the most unintended consequences, because we have this vapor drive that all of a sudden starts creating issues. But more and more we're looking at in building sciences getting to dryability, and that's what we'll talk about, the WUFI profile as the last thing we're going to talk about. And what that does is it evaluates your entire building assembly, not just it does evaluate where the thermal control is and where the vapor drive is, but it evaluates the ability of that wall to dry. And I say that just when you talk about the airtight drywall approach, and it's nearly impossible to get a complete air barrier. There are just too many, in a building, there are too many penetrations. We can certainly get fairly effective, but to get a complete absolute air barrier is extremely difficult. It takes diligence in the installation. It takes a significant detailing in design. And so backing off of the concept of trying to get walls completely airtight is making sure that we're accounting for moisture that can get in the wall and allowing it to dry. We'll talk about that more in just a minute. So the last part of the thermal envelope, and we spend a whole bunch of time really looking at details and different ways to get the most efficiency in our walls, and we went through a bunch of those from exterior foam insulation, double stud walls, SIPS panels, ICFs, all these ways to get really, really tight, really, really low air infiltration in our wall systems, and then the next thing we do is cut all these big giant holes in them. So windows and doors and where we put them and how we select them are fairly important. And it's in your book, I won't spend too much time on it, but the one thing about windows and doors is they lose heat in 4 different ways. All 3 of the convection, conduction, radiation, and straight air leakage. Even without a convective current, windows can leak air. And you think about it when you're standing next to a window. If you're standing next to a window on a bright, sunny, cold winter day, you stand next to that window, you might be able to feel some drafts coming through if it's leaky or it's not properly insulated around it. If you put your hand right on the window, you'll feel that conductive heat loss. And if you stand back from it, you may be able to feel the radiant warmth coming through from the sun. Inversely, when the sun goes down, that window is radiating heat straight out. So the window and door selections that you make in your thermal envelope and how you install them and seal them is pretty significant. Briefly go through the different types of windows and wood, vinyl, aluminum, and fiberglass, and there's a few others, composites, but they all have a little bit the pros and cons of each one of them. Wood tends to have better thermal properties sometimes, but it's got a lot of maintenance. It's also more expensive. There's a range of vinyl and aluminum window manufacturers. In this climate, we don't necessarily see aluminum. You remember the material in our little K value table that has the highest K value is aluminum. Why they ever started making windows out of it, I have no idea. But and then various glazing options, and we'll talk about these a little bit in a minute. Yeah, so again, look at this in your book, but the whole, I don't want to dive down too far into windows. If you have questions on them, let me know. But the way that windows are rated, the National Fenestration Rating Council puts the window values together, and they're weighted as a weighted average of performance at center of glass and performance at edge of glass. So ideally it gives a representation of how the window performs, and the lower the U value, the better performance the window it for the most part. Sometimes the solar heat gain coefficient, it will, depending on the climate zone, solar exposure, it can help the performance of the window, and this can become important, especially when you're talking about passive solar and passive house design in general, because you may, in order to get the greatest efficiencies out of it, you may end up using different windows on different sides of the house. So if you're trying to take advantage of that solar gain on the south side of the house, you may actually use windows that have a very high solar heat gain coefficient, because they're going to bring in more of that solar energy and hold it back. So you're going to get more gain out of those windows. Whereas on the north side and west side, you may not. You may be dropping down to a window with lower solar heat gain coefficient. But basically, windows are primarily gauged just on the U value. Current code right now in Montana, they've got to be a .30 or lower. And you've got a little chart in your book that has the U value, standard U value for representative windows. And if you really want to see why they're so important in overall thermal performance, take all the U values that they give you and convert them to R values. They're not very good. So, window performance continues to get better. I don't have the other slide in there. But we're still looking at even windows that have, so code, if we're at .30 or better for code, we're looking at about an R 3.1 window. So again, spending the time, the energy, the effort to get the building envelope as tight as we can and as efficient as we can, windows become the biggest loss. So did you all read, you go through your book, do you understand how low E windows work? They reflect those longer, I just lost my train of thought. They reflect the longer waves back out at certain angles, but they allow them in. And so what they're doing is they're trying to block against excessive heat gain when the sun's high in the sky, and then they're trying to allow that to come in when we've got the winter sun. So all low E is a coating. They put it on windows. Usually it's in between the panes of windows, and depending on, for example, here in our climate, we'll put it on S3, which is, if you start from the outside, they go S1, 2, 3, 4 in a double pane window. We'll put it on S3 because we're trying primarily to take advantage of the heat gain and hold that heat in. If you're primarily in a cooling climate, windows will be manufactured and they'll be putting that low E surface towards the outside. Sometimes they'll actually put it on, they'll use a hard coat on the outside. But it does make a difference and increase the thermal performance of the window. But again, even going from a .3 to a .2 window, you're still just increasing your R value from R3 to R5. So decreasing the amount of windows and where you place them. And so I talked about the heat gain. Just the inverse of that is in cooling climates, you want to avoid that. So inversely, you won't be putting more glazing on the south facing. Choose building orientation to maximize efficiency. Again, just that little 15 to 20 degrees within south-southeast is significant on the efficiency of it. Shading, which is also part of daylight modeling, again, to avoid overheating. You can do it structurally within the building. You can do it simplistically with vegetation. But where you put the windows in the thermal envelope and how you install them is significantly important. Anything, skylights and doors, anything anywhere we've got a hole into the building envelope is a weak point. Understanding when it comes to energy modeling and weatherization, again, windows can be a significant loss of energy, but we look at it from a cost-effective point of view. It may not be the best thing to do. One of the things we're going to try to do with our blower door testing is make some energy improvements, and we're probably going to make several levels of energy improvements to the house, but we're going to have a budget. So obviously if we go in the house that we're going to work on, we hopefully try to get 2 houses, but it's about 20, maybe not, 18 years old, and so the windows that were used were at the time probably windows that met code. They're probably a U value of about 0.4, maybe 0.42. Probably if we look at straight energy gain, if we went in and replaced all the windows, it would probably give us the largest decrease in energy usage. But I think we'll find a bunch more other cost-effective ways to improve it. So, any questions on thermal envelope strategies? And I know we spent a lot of time on them last semester, but as systems go, it's probably the most important system in a building, that separation between inside and out. All right, let's take another quick break, and then we've got one short section to kind of wrap up thermal envelope design, and then we'll be done.